Hello everybody, here's your video on the rational root theorem. Now let me introduce the idea of the rational root theorem and why we would even use such a theorem. So let's think about the following scenario. I'm going to give you a polynomial right here. It's going to be a cubic and there's not any placeholders here. And I'm going to tell you I want you to solve this. So that means you have to find the x-intercepts. Well, if you look at this here, you definitely can't do grouping because even if you take a 2x squared out of here, that would leave an x plus 1. You could factor a negative 1 out, but these are definitely not going to be the same. So you can't do grouping. And you definitely can't factor a GCF out because all these terms don't share anything in common. So in order to solve it and in order to break it down to a quadratic, a second degree, you're going to have to use synthetic division at some point. But the problem is I didn't give you any factors to start with or any zeros. So the question is, how are you going to actually break this thing down into a quadratic? Now, normally what would happen is you would do synthetic division and you would put your numbers in and you would be given a number to put right here and you would want a remainder of 0. But the thing is, I didn't give you anything and I'm not going to give you anything. So you're going to have to decide what number should go here. Now what you could do is say, all right, I have a lot of free time, so let me just start with a number line and start picking numbers from here, and it could even be a decimal like 1.1, and just try numbers over and over again until you get a remainder of 0. But that would be very, very time consuming, and no one really has time to spend that much time. So mathematicians came up with a rational root theorem that will give you a list of possible zeros to try, and it will greatly reduce how long it's going to take you to get a remainder of 0. So I'm going to show you the rational root theorem, and I'm going to tell it to you in a general way so it applies to any polynomial, and then we're going to try it out with a couple so that you get the idea of how it works. So make sure you're writing your notes down here. Pause the video if you need to. So here it is. For the rational root theorem, I'm going to take a general polynomial, and don't let all these letters intimidate you or confuse you. All this means is I have x's and they're going down one by one in degree until you have just x to the first and then no x. And then these letters here just represent the coefficients. And I really don't know how many there are, so I might need more letters in the alphabet than going to F and G. But the point is, like, these are just coefficients. And when you do the rational root theorem, the most important numbers are your leading coefficient. So label this here as leading coefficient, and this one here is your constant. It's always going to be at the end. That's the definition of a constant. And here's how the rational root theorem works. We're going to assign the leading coefficient and the constant letters, so the leading coefficient is given the letter Q, and the constant is given the letter P. Now, I'm not sure why they chose these letters or why they chose to make Q come before P. But that's how they gave it. And every rational zero, every possible rational zero of f of x is going to be in the form p over q. And whenever you write it out, p is going to go on top of q here. And you're going to write out all the factors of your constant term, which is the constant at the end given the letter p. And q, you're going to write out all the factors of the leading coefficient, which is given the letter Q, the first number at the very beginning. Now, if you get confused remembering that Q comes before P, what you can think of is that in England, instead of saying the word line, like a line of people, they say a queue of people, and you can remember the following. You have to wait in the queue before you can P. So Q is going to come before P. And I know this is probably the most ridiculous memory tool ever, but honestly, I always think of this whenever I do it myself. So if it's going to help you, remember that. And if you think it's weird, then come up with your own way to remember it. But we're going to apply this to the following polynomial. I'm going to take this cubic here, and this is Q, and this is P. So all our possible zeros are in the form P over Q. So what I'm going to do is I'm going to take our number P here, and I'm going to write out all the factors of it. Now, 12 has quite a few factors. 1, 2, I always write them in order, smallest to largest, and goes up to 12. Now, the thing is, 12 can be divided by positive or negative 1. So you need to always consider the positive or negative. And then Q, factors of 2, is just 1 and 2. Now what you have to do is write this out so you get one long line of possible zeros, and those are the ones that you would put here and test. So instead of having infinitely many numbers to test, you have a finite amount of numbers to test. So what you're going to do is you're going to take all your numerators and divide them by 1, and that will just give you the same numbers. Now, you're probably wondering, do I have to write plus and minus in front of every single one? And the answer is no. Just put plus and minus in the front so that I know that you know to do plus or minus. Then you're going to take the numbers and put them all over 2. Now, don't repeat numbers, okay? If I do 1 over 2, that's going to give me half. 2 over 2 is going to give me 1. Well, I already have 1. Don't repeat it. The list is going to be long enough. Then you have 3 over 2. That's a new one. 4 over 2, I already have it's 2. 6 over 2 is 3. I already got it. 12 over 2 is 6. I already got it. So that means I have 2, 4, 6, 8, 10, 12, 14, 16 possible zeros. And you would test those out one by one, and you're going to hope that you're lucky and you pick one that works soon so you don't have to test all 16 of them. Now let's try another one here. So here is Q, and here is P. So you're going to do P over Q. And once you get the hang of it, it goes a little bit quicker. So P is the number at the end, so I'm going to put all the factors out. And then Q is plus or minus 1 and 3. Then you just divide them like we did before. So far I divided them all by 1, and I got these numbers here. And then what I'm going to do is divide them all by 2, and that's going to give me just a few more here, or divide them all by 3, I'm sorry. So 1 over 3 is 1/3, 2 over 3 is 2/3, 3 over 3 I got it, 4 over 3 is new, 6 over 3 is new, I have it, and 12 over 3 I have it, it's 4, which is right there. So 2, 4, 6, 8, 10, 12, 14, 16, 18 possible zeros this time. So let's just do one more real quick so you get the hang of it. Now normally when you do this, your first number will be smaller than your last number. That's just how books usually create their polynomials. But Q can be larger than P, and when you do that, you'll have more than 1 or 2 numbers in the bottom. But it's really the same exact process. If you divide all these numbers by 1, you get the same numbers. If you divide them by 3, you get 3 new numbers. And if you divide each of these by 9, you get 3 new numbers. So this time, none of them are going to overlap, and that's going to give you a big set of numbers to pick from. So let's go ahead and actually apply this to a polynomial. But one more time, I just want to emphasize, these are possible zeros. It's not like all of those are going to give you a remainder of 0. Because remember, just look at the degree. This is a degree 3, so it has 3 zeros. Only 3 from this list can work, maximum. So just make note again that you have to test these out one by one to see which are actual zeros. And when I say test them out, I mean use synthetic division until we get a remainder of 0. And that's how you know it's an actual 0, and you can use it to break down the polynomial. So let's go ahead and try this out with a polynomial. I'm going to give you one that is a 4th degree. So let's do x to the 4th plus 4x cubed plus 3x squared minus 4x minus 4. And again, the point of this is to do it without any technology, which is why we are going to do the rational root theorem. You could just graph it on a graphing calculator and see what the x-intercepts are, but we want to be able to do it without the graphing calculator. So I have q comes before p, and if q is 1, that only leaves me 1 in the bottom. So this is going to be nice because I really won't have hardly any to choose from. Just 6 possibilities here. So it's going to be quick. And what you always start with first is your original polynomial. And again, I don't know which of these is going to work. So I'm just going to go ahead and try, let's try -2. And again, we're looking for a remainder of 0, 2, -2, 4. Oh, we got it. Remainder of 0. Hooray! Now this is a cubic. So I still have to do synthetic division one more time. Let's try another number here. Let's try 4. Why not? So let's bring the 1 down. 1 times 4 is 4. 24. This isn't really looking too good. Yeah, this is definitely not going to work. So that's whenever you would set up a new synthetic division. Or if you have an eraser, you can just erase it. And let's try another number. Let's try maybe -1. So when you get good enough at this, you can kind of look at these numbers and see what kind of number you're looking for. Because like here, the number got really big. It obviously wasn't going to work. once you do it enough, you'll get better at it. Okay, hooray, we got another one. Now, our resulting quadratic is x squared plus x minus 2. That'll be nice and quick to factor. And don't forget about the two factors you already found. 4 did not work. -1 worked, so that leaves me with x plus 1. And -2 worked, so that leaves me with x plus 2. So all I have to do is write this in fully factored form. So 2 and -1 multiply to -2 and add to 1. And then I still have this. Whoa, multiplicity! Look at that. X plus 2 squared, x minus 1, x plus 1. Good thing we know what multiplicity is, right? So I have -2, 1, and -1 as my zeros. It's my y-intercept. My y-intercept is -4. And let me plot these and see what kind of extra point I'm going to be looking for here. So draw a little graphing grid for yourself. I realize you might not have one of these in your notebook, but just draw a little grid and put some tick marks on it. Don't forget the tick marks. So -2, -1, woo, these are close together, and 1. My y-intercept was -4. My end behavior, let's see, even degree, positive leading coefficient. Both ends are going to be pointing up. Well, look, my x's are so close together that if we really wanted, we would have to pick an x value in between them. I really don't feel like doing synthetic division with a decimal. So in this case, it would be okay to pick a number outside of, normally you're supposed to pick one in between the x-intercepts, but they're really close together. So let's just pick 2. And the extra point won't really help us that much, but just so we can practice the remainder theorem, let's find out what kind of remainder we're looking at. 6 times 2 is 12. That's going to give me 15. That is going to be 30. And then 26. And then 52. And 48. So that's really just telling me that at 2, I'm way up at 48. This is a really narrow parabola. Wow, not a parabola. Really narrow polynomial. So let's connect this. I'm going to start from the top. And, okay, -2 is the one with multiplicity. This has multiplicity of 2. So that means it's going to bounce off of that x-intercept. It's not going to pass through it. I have to quickly turn around to pass through 1, go through my y-intercept, I pass through -1, then I pass through 1, and there we go. So really, it's the same exact process as before. It's just that you have to test for yourself to see which x-intercepts work. Here are your 2 u-tries, and just keep in mind, it's the same process we've been doing the whole time to graph a polynomial. You just have to do p over q first, like I did here, and you're going to pick them until you get 2 that work. So then you end up with a quadratic, and then you can keep factoring like normal. So write these down, graph them, show your workout, and then we will do practice on the whiteboards when I see you again. Bye-bye.